Hello all, welcome back to EDA Logics. In the previous class, we have discussed about the theoretical concepts related to the Verilog hardware description language. From today's class, we are going to discuss about both theoretical and also practical in parallel. Okay, the theoretical part not yet completed. Okay, now what I am going to do is I am going to continue the theoretical part in a way which it is going on. Okay, and also I am going to from today onwards I am going to discuss about practical concepts also, how to write code for our designs. Okay, I'm going to discuss that part as well. So basically I am going to use EDA Playground, which is very easy to use it because it's a website. It doesn't require any storage, and it is very simple to run the codes and their TBs. Okay, yeah, let me explain about this EDA Playground. Okay, the right side where you can see the design.sv, which is a file. Okay, here we are going to write our design code, and the left side, if you can see, we have testbench.sv. Here we are going to write the test bench, okay, for our design. So and also we have tools and simulators. Okay, we need to select either one of the tool. Okay, among this, usually we prefer first one. Okay, usually we prefer first one. You need to write the code over here and the TB over here, and then save those using this save button, and then you need to run the code. Then you can able to see the output in two ways. One is you can see the output in the log file, which is visible over here, or else you can see the output using the waveforms as well. For that you need to include some of the lines in the code which will make you to see the waveforms. Without any delay, let's discuss about today's project or the today's design code. Okay, today I'm going to discuss about design of not gate using gate level model. Okay, total we have four levels of abstractions. Those are switch level, gate level, and then data flow, and then behavioral model. Okay, we are having four levels of abstractions. First, today we are going to discuss about how we are going to write the design code for the not gate, and we are going to verify it using the TB as well. Okay, in the gate level model. Okay, so any design code will be lies in between module and end module. Okay, any design code of any design that is going to lie in between module and end module. After module, you need to give the name of the module name. Okay, I am going to give the name as not yet, and you need to open the parenthesis. Okay, in this parenthesis, you need to give the input and output port list. You need to give the input and output port list. So for that, you need to have an idea about how not gate looks like. The not gate will be looking like this, right? The not gate will be looking like this, which has one input and one output, right? Let us assume the input as A and the output as Y. So we are going to assume input as A and output as Y. So we are going to give those details over here. The input is A, comma, okay, output is Y, and after closing the parenthesis you need to specify the semicolon. You shouldn't forget specifying the semicolon. Okay, completed. Now we have declared we have given the port list, inputs and outputs. Now after this semicolon to end module, we need to specify our code logic. Okay, since we are going to use the gate level model, in gate level model we are having by default primitives. Primitives are nothing but the keywords for each gates. For each gate we are going to have primitives. For not gate, the primitive is not. Whenever I am going to type the not, you can see over here it is highlighted, right? It is highlighted, right? It means it is a keyword which does the not operation. Simply does the not operation, and then space. You need to give the instance name, any name. Okay, I am going to give n not, and not. Okay, and open the parenthesis and close it. In this thing you need to specify what is the output followed by the inputs. Okay, what is the output for our design? The output is y, right? And the input is a, right? So I specified both input, output and input. First you need to specify only the output. Why? Because for any gate you are going to have only one output, right? So that we are going to specify the output first, followed by input. Okay, this is our complete design code for the NOT gate using the gate level model. Now let us develop the TB. Okay, the TB is developed in the tb.sv. Okay, so we are going to give module, and any TB is going to written in module and in between module and module. Okay, Verilog TB. This is the Verilog TB. Okay, so let us give a name for the TB as well. Not gate TB. Okay, and then you put just semicolon, or you need to open the parenthesis and close it and give the semicolon. Okay, we don't specify any of the uh, list over here inside the parenthesis. Okay, next, what we are going to do is, in the design we are having inputs and outputs, right? In the TB we don't have any inputs and outputs. We have only test cases, input test case and output test case. Test cases and test vectors we are going to have. Okay, what are the inputs in the design will becomes as rich data type in the test bench, and also what are the outputs that we are having in the design module will becomes wire data type in test bench. So that what is our input in our design is a, right? So it is going to become rich a. Okay, semicolon. And then what is the output that we are having in the design is y, right? So it is going to become wire y. Okay, now we have given both input and output test cases, right? So now what we need to do is, we need to instantiate the design module into the test bench. Okay, then only we can able to apply the test vectors to the design and get the respect to output, and check whether our design is functionally correct or not, right? So that we need to instantiate this particular module into the test bench. How we are going to instantiate? First we are going to take the module name. What is the module name of the design? That is not gate, right? So we are going to write not gate. Okay, now we are going to give instance name like we have given over here, right? We are going to give instance name. Okay, give the instance name some n not. Okay, and then open the parenthesis. Now we are going to specify the list over here. How you are going to specify the list over here means, there are total two ways of uh, specifying the list over here, in which I am going to discuss the first way in this class, and the other way will be discussed in some other video. Okay, now let us see one of the style. See how you are specified the port list in the design. First we have specified the input a followed by output y, right? In the similar way you need to specify in this in the similar way you need to specify in this module instantiation as well. First we have given input a and then output y, right? So we are going to specify test case a and y. and then close the parenthesis, put the semicolon. So this is how we are going to instantiate the design in our TB. Okay, we have given the test cases, and also we have instantiated the design in our TB. Now what we need to do is we need to apply the values to our inputs, that is values to our input test case, and we need to observe the output, right, respect to output. For that you need to use initial block. Why we are going to use initial block only means because initial block will executed only one time, and we also need our test cases needed to be applied to the design for only one time, right? So that we are going to use the initial block. When you are going to use the initial block, if you are going to write only single statement in the initial block, then you doesn't need any begin and end, which are similar to the flower braces in the C language. But if you are going to use more than one statement, then you need begin and end. Okay, now I am going to use more than one statement, so that I am going to use the begin and end. In this you need to give the input test cases. What is our input? A, right? We need to give different values of a. A is a how many bit input test case? It is 1 bit input test case, so that it is going to have two different values, that is 2 power 1 is equal to 2, right? It is going to have two different values, those are 0 and 1 only. Okay, this whole thing will be known in the theoretical part. Okay, yeah. So I am going to give a is equal to 0, that is 1 tick b 0. 1 tick b 0 means we are going to assign binary 0 which is having 1 bit size to the a. Okay, we are going to assign 0 which is having 1 bit size, which is of binary data type, right? So we are not going to give simply like this. Why? Because we need to include the delays as well, on which particular time you need to assign 0 to a. At 0 nanoseconds I would like to assign a is equal to 1 tick p 0. You need to keep the semicolon. Okay, what is this hashtag 0 mean? At 0 nanoseconds you need to assign a equal to 1 tick b 0, and you need to observe the output. Okay, similarly I am going to use hashtag 10. It means at 10 nanoseconds point of time you need to assign a equal to 1 tick b 1. What is meant by 1 tick b 1 means we are going to assign 1 to the a which is of 1 bit and of binary data type. Okay, now binary data type. Now we are going to specify some delay, some additional delay. So I am going to specify some additional delay, some 30. Okay, 30 and then semicolon. Okay, and then semicolon. It means the simulation will goes up to 30 nanoseconds, and I am going to stop this particular simulation. For that you need to use a system task which is $finish. Okay, first what happening is at 0 nanoseconds point of time we are going to assign a equal to 1 tick b 0, and at 10 nanoseconds point of time we are going to assign a equal to 1 tick b 1, and we are going to observe the respective outputs at their respective time instant, right? Respective outputs of y at their respective instant of time. Okay, and then we are going to run the simulation up to 30 nanoseconds of 30 nanoseconds time instant, and then we are going to stop the simulation using the $finish. Okay, this is how the code works. Now we need to observe the output in the log file, right? What I have told, we are going to observe the output in the log file, right? For that you need to write, for that you need to use the system task dollar display or dollar monitor. I am going to take another initial block, okay, above this particular initial begin block, okay, initial begin and then end. In this initial begin and then end, I am going to use dollar monitor. What does this dollar monitor does is, after reading this I am going to tell you, okay, don't worry. Open the braces. E, let us take time is equal to percentage 0t, percentage 0t, and then a is equal to percentage 0b, which is of binary data type, and percentage 0t is time, and then y is equal to percentage 0b double quotation comma. I'm going to give the parameters for all these format specifier. First format specifier is percentage 0t. For this we are going to use the system task, that is dollar time. What does this dollar time does is, it is going to print the time. It is going to print the time, time of instant. Okay, for example, we have told you, right, at 0 nanoseconds of time we are going to assign a is equal to 1 tick b 0. Okay, at that same point of time we need to get y is equal to 1, right? Why? Because it is performing not operation, right? Whether we are going to get at the same point of time or not, we need to know, right? So that we need to print the time as well. So that I am going to use the dollar time. Okay, it is going to print the time, time instant, and then I have used the a is equal to percentile b. We need to print the value of a. Similarly, respect to output y, and then close the parenthesis and put the semicolon. Okay, now you may have a doubt that I have written only $1 monitor statement, but I have given two test cases, that is a is equal to 1 tick b0 and a is equal to 1 tick b1, right? We need to write $2 monitor statements, right? Like this, any one of you may get a doubt, right? But we shouldn't write $2 monitor statements. Why? Because what is meant by dollar monitor means, it is going to monitor in the sense, it is going to check every time what are the values specified over here. If any of them having the change in them, if any of them having the change in them, okay, if any of them having the change in them, then it is going to print the statement in the console. For example, initially have assigned a is equal to 0, right? It is going to print the um, print the result in the console for the change of a is equal to 0. Okay, and then I have made a is equal to 1, right? It means a is getting changed from 0 to 1, right? After becoming a equal to 1, we are going to have some other result which is quite opposite to the previous one, right? It means what does this dollar monitor knows is, there is a change in the input a, so that we need to see that change and we need to observe the output and we need to print again, so that this dollar monitor think like that and it is going to print second time as well. Okay, then what is meant by dollar display? Dollar display means it is going to print only one time, it is going to observe only one change. If you are going to write dollar display over here, $1 display over here, it is going to print when a is equal to, it is going to print when a is equal to 0. Okay, it is not going to observe the change of a is equal to 0 to 1. Okay, it is not going to observe it, but dollar monitor observes it and prints whenever there is a change in input. Whenever there is a change in input, it is going to print thus many times. If the input is changed from changed 4 times, it is going to print 4 different outputs for the 4 different changes in the input. Okay, so this is how the dollar monitor works, and this is the difference between dollar monitor and dollar display. Don't worry, when you get an output, you can able to understand it. So let me save the code. After saving, you must run it. See, you can see the output in the log file. Okay, see, you can see the output. Time is equal to 0. At 0 time instant, a equal to 0, and correspondingly we have the not operation of a, right, which is y is equal to 1. We got the output, right, at time instant 10 nanoseconds. Okay, we have applied a is equal to 1, we got output y is equal to 0, which is the not operation of a, right. That is our required output, right. See, at 10 nanoseconds we are applying a is equal to 1, we are getting y is equal to 0, and at 0 nanoseconds we are applying a is equal to 0, and we are getting y is equal to 1. This is our required output, right. Yeah, now we have got console output. I hope you understand this point very well. See, we have used only $1 monitor statement, right, but we have got printed 2 times. Why? Because there is a change in input 2 times, that is 0 and then 1. For the input 0, it is going to print 1 time, and for the change in input from 0 to 1, it is going to print another time, so that the output gets printed 2 times when using the dollar monitor. Okay, so this is how the code works. Now how you need to see the waveform. Okay, now we got the output in the text format in the log file, but how if you need to want to see the waveform? That thing I am going to discuss now. Okay, see, we need to include 2 lines. Let us include those 2 lines after the dollar monitor. Okay, what are those 2 lines are? These are the 2 lines. We need to include 2 system tasks. Those are dollar dump file. In the dump file, we are going to give the name of the dump file, some random name. Otherwise, you can remove this particular name and give notget underscore tb dot vcd. Okay, and then semicolon, and we need to give another system task, that is dollar dump wires of 1 comma instance name. What is the instance over here? Not get underscore tb, right. We need to mention that name. Okay, that is not get underscore tb, not get underscore tb, right. So after that, you need to save the code by clicking the save button, and you need to select open ev wave after run. You need to select this, and then you run the code. Then you can able to see the waveform. Automatically you can able to see the waveform. So this is the waveform. Okay, we're having input test case, that is a. Initially it is 0 at 0 nanoseconds time instant till 10 nanoseconds time instant. We are we have we can observe the output, that is 1 from 0 nanosecond time instant to 10 nanoseconds time instant. After that, a is becoming to 1, and it continuing till up to 30 nanoseconds. We can see over here. Okay, 30 nanoseconds and more. Okay, and more, and we are going to observe the output 0 from 10 nanoseconds to 30 nanoseconds and then more. So this is how we can observe the waveform. This is how we can observe the waveform using the EDA Playground. Okay, and we can also observe the log file, that is console output over here. At what time instant what input value is and corresponding output value is we can able to see over here. Okay, so this is how we are going to see the output using the EDA Playground, and this is how we are going to code in Verilog for our respective design. So just you guys try it once. Okay, all these concepts will be discussed by me in the theoretical part in very detailed manner. This is practical session, so that I am discussing that I'm discussing in a way that I hope you guys know everything, or you guys have a little bit of knowledge on Verilog, so that I'm going to discuss in that way. Okay, so just have an hands-on experience. Thank you guys.